Hey everybody, this is Larry. This is day 30th of the Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. Today we have 2699 modified graph edge weights. It's a hard problem, so we'll be here all night maybe. Maybe not, hopefully not. And if I do this, if I finish this early, I'll maybe look to do one more bonus problem. I am a little bit sleepy, maybe not that sleepy. I ran 10 miles today at the marathon pace. But it was too hot outside, so I think my body was just not handling it well. I was like so, I don't know why, it's just so painful for today. Which is kind of bad, right? Because if I can't do 10 miles at marathon pace, how can I do 26 at marathon pace? So anyway, but yeah, so me rubbing my eyes aside, let's take a look at today's problem. You know, my quads are, not quads. What is this? Whatever, some part of my leg is a little bit achy. Anyway, okay. You're given an undirected weighted connected graph containing n nodes labeled from 0 to n minus 1. There's an integer array edges where edges of I is a, b, and is it directed? Undirected, okay. So there's an edge, and then some edges have a weight of -1, while others have a positive weight, which can be any number. So, okay. Your task is to modify all edges with -1 by assigning them a positive integer values in the range 1 to 2 times 10 to the 9, some big number, so that the shortest distance between the node's source and destination becomes equal to an integer target. Okay, maybe. If there are multiple modifications that make the shortest distance between source and destination equal to target, any of them will be considered correct. Return an array of all the edges in any order that makes it possible to make shortest path from source to target and empty. Do they have to be distinct? No, just any number. Okay. Let's see. And it has to be exactly target, not okay, so this is, yeah, there's no modification, right? Oh no, there is a modification. They just didn't show it before. I see. Okay, and from 0 to 2 is 6. I'm also wondering, the shortest distance. I was gonna say, like, you can do like some weird thing, right, with like going back and forth, but if it's the shortest, then you know. Okay, n is 100 is interesting actually, because honestly my first inclination was to do a binary search. Basically binary search on actually I guess you can make, there are more than one edges, so maybe that doesn't make sense. Maybe I'm wrong on that actually, but I had, my first idea was some sort of binary search idea where, you know, you can adjust some stuff, but maybe that doesn't make sense. But n is equal to 100 is interesting because that's more, right? So the first thing that I think we have to do, or should do in either case, is just write the shortest path algorithm, right? And given that there are n and e edges, right? You know, you can just do a regular dice juice algorithm, which we already talked about last couple of days. So it's going to be relog e. Maybe I should do a separate video on dice juice and how to kind of get it correct. Because I feel like I get a lot of, not all the time, but every once in a while. Yeah, but yeah, okay, so I'm still just thinking through this a little bit. So again, we have relog e, and then we have a lot of edges that are possible -1, right? There are no additional constraints. First thing I guess I want to do is still, you know, we still need an adjacency list anyway, so let's set that up. Though I'm not gonna lie, I don't know what I don't know how to solve this right now yet. But so yeah, and I know that I do have some variation of dice trace in the back of my thing, right? So okay, so the first thing we have to do is check out whether it is impossible, right? Empty way is impossible, right? Yeah, it is impossible if the shortest path is already shorter, because you're only going to add edges. Or I mean, yeah, I think that another way of thinking about it is that the -1 is kind of like adding edges, but so yeah, so if you do a shortest path, if it's shorter than target, then it is just not possible, right? But what will make it possible? I'm trying to think whether I can be like really lazy on the greedy. Alright. So okay, so for example, if we start with, okay, so let's take some notes first, right? So if we do a shortest path thing, dice trace say, right? And shortest path is lower than target, or shorter than target, then it is not possible, right? And then now we want to see if it is possible. And then another thing is that, okay, and maybe we can do this both on the same thing anyway, but if we convert all the negative ones to 1 and calculate shortest path, if shortest path is shorter than target, then it is not possible, right? Because you have to set them to be at least 1. So because that's the lower bound, right, of what they want. So we don't even have to do this per se, because this supersedes, or is a superset of this thing, right? Okay. So then now, what happens if it's possible? That means that we can adjust. I mean, I want to say, and I don't know, I'm still trying to work out the details in my head, honestly. Which is that, okay, then now we know the path that we took, right? We know the shortest path. Can we convert one of the previous -1s, which are now 1s, to a bigger number, right? And if we do, what would that look like? Like, then now we have to construct another shortest path, right? I mean, at least that's what I would have been trying to do. And then if we try to do another shortest path, then what happens? Then either it's still shorter and we change another -1, or no, that doesn't make sense. Or it would never be shorter, because you would just adjust that 1 to be whatever the difference is, right? And see if it is still the same shortest path. But I don't know, because I feel like okay, yeah. I just want to make sure that it is a multi-answer thing. Yeah. And then if that doesn't fix it, meaning that now your shortest path is your second shortest path, or maybe just not your shortest path, then you do it again, right? But in theory, there can be ye -1s, right? And if we do the dice trace algorithm, which is re log ye on all of them, then this is going to be ye times re log ye, right? And ye, of course, is going to be, I mean, I want to say 100 square, but technically that's, you want to be more precise, it's going to be 100 choose 2, which is, 5,000, right? Is it? Yeah, maybe 5,000. I don't know, math is hard. So ye is 5,000, right? Max ye is equal to 5,000, unless I mean, they mentioned it here, okay. We could be 100. So this is already 500,000, right? Log year is what? Log year is, what is that? 10 is so like 12 or something. So this is kind of like cutting it close. It feels like, honestly, because that sums up to like 6 million ops or something like this, right? Of course, there are other. It's not, you know. Are they? And then my question is: are there always an answer? And I think I'm trying to also think about a termination proof. I would also say, just as a disclaimer or maybe a caveat, during a contest, I might YOLO try this, honestly, because it feels, I don't know, but for now, in a more deliberate, like let's say I'm in an interview setting, I'm still thinking like, okay, can I prove termination? Well, I mean, termination I guess is easy to prove. Well, yeah, because basically, if you modified one edge from, so -1 to 1, but then 1 to the number, that means that either, sorry, I had to take a little bit dehydrated. That means that okay, so let's go back a second, right? So we convert one of the -1 to 1, or well, we convert all of them to 1s, but to 1 to the delta, which is the delta between the target, right? So then now there are only two cases, right? Which is that edge is in the shortest path, which means that we have target and we're done. Or if it is no longer in the shortest path, then it will not show up again, right? And the reason is because the reason why it won't show up again is because then now you know that there is a path such that there is a path such that we have the target, if that makes sense, right? Then it will not show up in the future because there exists a path in which the total rate or whatever it's called will be target. And another way of thinking about that is that if you raise all the other variables to greater than the target or whatever, then you have that path left. It's technically not true because that path may contain multiple ones or multiple whatevers, but I think that's like that's sufficient to show that you will never edit the same edge more than once. So this is the upper bound, but it's a tough. I don't know that. I think most of the time you don't need to hit that upper bound, but it's still like a hard sell for me to tell that it is fast enough. And I'm yeah. And I think I messed up here, actually. No, yeah, I think I said the wrong things here. If the shortest path is shorter than target, then it is not possible. This is not a superset of this, because actually what I mean here then now is that if the shortest path is longer than target, right? Because if it's shorter, yeah, it has to be shorter for you to change the 1 to a thing. Otherwise, you know. So okay, so I messed up here. My fault. I mean, I know that I'm like a few minutes late on that one, but yeah, this is a hard problem. I mean, I'm already 15 minutes in, and I don't think I'd waste that. I mean, you know, I'm obviously explaining a little bit, but I don't think I waste that much time. Huh. Is it enough for us to start? Because it could be a lot of negative ones. Let me take a look at the problem again just to make sure that I didn't miss anything. Positive. Oh, you never choose 2 times 10 to the 9 because that's bigger than the target. That just seems a little silly, but okay, fine. I mean, yeah. And now, yeah, I mean, okay, let's just YOLO try this. I'm not, honestly, I'm like half confident, but not that confident. That'll be fast enough. Maybe this is one of those problems that maybe I have to change to another language because Python is weird, but I don't know, we'll see. Right, so here we'll do a thing, right? Might have to have a better data structure here. Let me think. Let me have to think. I think I think there's also another way to solve this, but maybe I'm here. But I have to think through all the implications. But I think because we're modifying an edge instead of a node or something, this is fine. I think there's another way to think about this, right? So let me bring up the drawing board. So okay, so let me think. I mean, so we have an upper bound. This is an idea, right? But let me give another idea a try. I clearly don't remember this one. In case I don't know if I might have solved this. I don't know, but I definitely don't remember another case. But yeah, so my idea is that okay. So let's say you have an initial graph. We just pretend the negative ones don't exist, and that's fine because we can always choose the negative ones to be 2 times 10 to the 9, which is over the target. So never be correct, which is in effective, it doesn't exist. Like we can make targets don't exist. So now let's say we construct a graph, right? So then now we have these things and you have like fake edges that we need to set, but they don't really exist, right? So then you have kind of these things. And the thing is that we can now do Dijkstra's, but minimize on 2 things, right? We can minimize on the number of I'm trying to think through the edge cases. So my idea is that, okay, let's say you have different components, right? So here you're trying to get from this one to say some on the bottom, and you have some edges or something like that. And here you have some maybe what I call fake edges, the -1 edges, right? So you have like all these edges. And if you want to minimize the number of red edges, do I want to minimize the number of red edges? I don't know. But maybe that doesn't make sense because but my idea was that, okay, let's say we're able to calculate the shortest path that goes through only one edges, but I guess in this case it's not possible. But okay, so two edges, right? That means that, and we, for whatever reason, we just set these to infinity, right? Infinity, 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 infinity. That means that, well, whatever numbers is, as long as this number plus this number plus this number is equal to target, then that's good, right? Oops, why did I use X in the same place? So, you know, because this one we can set this as 1, I mean, whatever, and then this one is just whatever, and then that'll be good enough, right? So like, let's say, you know, this is 10, this is, we have to set it to something as 1, and let's say we just want 12, then we just set this to 1 and it'll be fine. Let's say we need 120, we set it to, what is it, 109, right? And that'll be fine too, right? Because that's a possible thing, and then we set the rest to infinity, and it'll never go through the other way because we only have one route, right? But the question that I'm trying to think, so actually this would, if the initial graph is disconnected, that's all we need, really, right? We just try to figure out the shortest path, and it doesn't even, I was going to say we want to minimize the number of ones, but I don't think it even matters. If the graph is disconnected, then we can just construct whatever we want. But the question is, okay, and now I'm trying to think through it a little bit more, which is that, okay, so let's say now we have connected graph. So then here we do right, maybe whatever, right? So let's say the blue ones are. So now we have some connected graph, and then we also want to do this, but. And again, we have to, of course, if the existing blue stuff has to be greater than, right? So then now we have to try to figure out how to incorporate these such that they are shorter. And I don't know that it is easy for me to figure that out, maybe. Right? If that makes sense. Because then now, we know that this, well, I guess if this is too short, then this is no bueno, right? Because if this is too short, then that means that we have no answer. So I said that wrong. I made the same mistake again, sorry. But okay, if this is too long, we have to try to figure out another shortest path that includes one of these. So okay, so first is that we will want Dijkstra, and we kind of filter out everything that is greater than target. So that means that we should, in that case, then we'll never consider this anyway. And then here, so either we get to here first, where this thing is longer because we just know, well, if, okay, sorry, let me, I have it in my head, but I have to say it correctly for y'all people at home. But okay, but I think what I want to say is that, so if we filter everything lower than target, then there are then there are two cases, right? One is that the existing network would get here, which means that either it's equal to target, which means that we don't have to change anything, or it is lower than target, which means that it is impossible. But if we do filter out, that means that eventually, if the graph is connected, even with the -1 edges, then we will get to it with a count of negative edges, right, as the shortest path. And my question is whether I can prove, I think that's the hard part, right, is that now, let's say let's say there's one edge and it's the shortest, but what if I think this is what takes a deep understanding of Dijkstra, right? Because Dijkstra assumes, as part of the greedy, Dijkstra assumes that when you're at a node, when you're processing a node, right, that that everything before that the process of getting to it is the shortest, right? So how do you incorporate it with the number of edges, the -1 edges? What if there are 5 red edges? How do you distribute the rate such that it gives you a unique? It doesn't have to be unique, but the shortest path answer, right? Because you can imagine, or at least without a proof, you can imagine that you can assign the weights in a way such that there is another shortest path that doesn't go through your red path, right? And then now what happens, right? Like for example, we can actually. If at least if you're not careful, maybe you can construct another way of doing it. But for example, if you have something like right, maybe something like this, right, and then now you have. Yep, and maybe this one is right or something, right? Now, if the target is big, you can maybe set something like, okay, let's say this is 1, this is some big number, whatever, big number, b, right? Big number, right? But then now, if you write it that way, then maybe it is possible that this big number is bigger than these 2 edges, and so that now the shortest path goes through here, which is not what you want. You want the shortest path to go through here, so then now you have to assign it, right? So I don't know if there's an idea in here, but I don't know that it is sufficient, or like I'm trying to figure out how to get around this or whatever. Here's a hard problem. I've done no work and it's been 28 minutes. Can I get around this if there are 2 edges on the shortest path? And also, if there's 1, is it okay? Even? If there's 1, then there are 2 things, right? One is either there's already a shortest path to it, so you don't care, and or that it's impossible. And then if there's 1 edge, then you would just set that to the target. Okay. But if there are 2 edges, then how do you do it? Like if we set this to 1, then now this is longer, right? So then now we want to set it to something bigger. But then what if... Well, I guess... Well, if there's only 1 edge in it, then it's fine. The answer is still like, okay, well, if there are 2 edges, how do you change them in a way such... I guess you just change them 1 at a time, right? As we said. Because we said it before. But if we change them 1 at a time... If we change them 1 at a time, I don't know. I mean, then now we're back to what we were working on. So that's why I'm like, okay, maybe this is the way to do it. Yeah, it's a little bit weird. I mean, yeah, like I said, if this was on a contest, I probably would have YOLO'd this. But it's still like very, not confident about it, honestly. I mean, I'm confident it is correctness. I'm not confident that it is fast enough. Yeah, let's just do it. I don't know. If it's wrong, then we'll try to figure out what to do, right? And oh yeah, what I was going to write, which gave me a little bit of that idea, is if this is -1, then how do we want to look? We want to, maybe names changeable edges. I don't know. That's too long, right? -1 edges. Weird edges. Alright, fine. Okay. I don't know. The bounds are very close, but okay, fine. Yeah, okay, fine. Yeah. Yeah, and this is gonna be just standard dice draw, so maybe I will do the version that we talked about the other day, right? What am I doing? Oh, from source. I think actually technically we do that only afterwards. Oh, why do I have H? Yeah. What am I? What is this? That doesn't even make sense. I don't think this is necessary, as I say, but what do we want? What do we want? When do we want it? Right, and then now, destination or something. right? Okay. So then now we can do a dice draw on the adjacency list, on the thing, and then now, okay, so D is equal to this. What was, if this is less than target, then we are not, it's not possible because we cannot add edges to make it less. If it is equal to target though, then we just change everything to whatever. If D is equal to target though, we could do a switch statement. I always forget how to do a switch statement in Python. Maybe I need to learn it, so let me actually do that here. Match. Okay, let's give it a, I need to like get used to it a little bit. Oh, but there's no like if statement matching, right? Like in some other languages. Let's see. Pattern. There is an if statement apparently. So I guess that's fun. Let's see. Then we just return adjacency list kind of. I mean, I know that I'm not waiting. Okay, let's just wait it out. Let's just return this for now, and then I just want to see if this works, honestly. Like syntax wise. Okay, that looks good. I mean, or at least it doesn't like be like, hey Larry, what are you doing? Stop doing it. Which happens sometimes. Okay. Oh yeah, I did actually, I was like, I remember to write that in before. Okay. So, I mean, yeah. Can I just break? Outside loop. How do I just ignore it? Is that fine? Maybe it's fine. Okay, fine. Yeah, okay, fine. Alright. Oh, so this was some impossible. Oh, yeah, that was this impossible one. And then if it's equal to target, then we just convert the edge list. So we just convert edges. So I think we have to convert to -1. So I think that's Yeah, I'm just like for I in range of length of edges. It's like edges of I, or if edges of I of 2 is equal to -1, edges of I of 2 is equal to what is it, 2 times 10 to the 9 or something. Alright, okay, so then now we handle those cases. Now we have to handle real cases, which I'm still not super confident about. But okay, first of all, we convert, we'll do this thing, right? We'll convert all the edges to 1s. I just realized that wedges is a word, but okay, fine. So anyway, yeah. For UV and wedges, maybe this should be a set, I suppose. Just because it's like very awkward to modify this now, right? Maybe I just write this as else. But then I have to change it later if we want to make modifications anyway. So how would that look? guess just int, right? Still doing the same thing. Okay, good. And then now we want to say, what do we want to say? That, yeah, adjacency list uv is equal to 1. And then we just, yeah, if I guess we'll do the same thing we do before. If this is greater than target, then we just return empty, because it's just not possible. Otherwise, if it's equal to target, then we're done. But I don't know. But this is like a special case. I don't even know. I don't know if I should be writing it out, but it's fine for now, I guess. Otherwise, we have to change edges one at a time. Well, yeah, this apparently worked for this one. So at least it's not completely wrong. Okay. Okay. So then now what? We want to say that the nodes and maybe wedges should be a set as well, though we have to be a little bit careful. Right. We just add a previous thing, right? So then now we have the edges. But then that would be a little bit clearer. Okay, actually it's not that bad. Why is it? Alright. So now I can just do this on the paths. I think. I hope so. Might have to add like parens for a tuple or something. Okay, looks the same in a good way. But then now I have to do something here, which is the D doesn't matter because D is less, but then now the previous will give us the edges. So yeah. We go back from destination, right? Path is equal to or from destination. Something like this, right? Let's just print it out real quick. Right, and this is on the first thing, which is going to be going from 0 to 1. Well, this is backwards, so yeah. I did it wrong. Because we constructed backwards. No God. It's just so annoying. How can this be right? Am I missing something weird? I'm probably missing something weird, but like I feel like I'm doing this like in a very complicated way. Like maybe there's a connected components problem that I don't even know about or something. Yeah, I mean, no, this is just a general graph. Like if there was a specific graph, like variation of a graph, like if it's a tree, for example. I mean, I know that a tree will make it too easy, but if it's like some specific graphs, maybe they'll be a little bit weird, but no, okay, well, and there's no constraints on -1s or anything. Oh. Okay, and now we take an edge on this path, or I don't know. It just seems hard. But I mean, maybe I just need to grind it. So now we have this path from, okay, 0 1430, which is the same either way, and it has how many edges? Or like what are the, so 0 to 3 is 1 to begin with. I'm still trying to think through what is the cleanest way. I mean, the other way is to like add the edges one at a time, right? Like we can set one of them to be 1 and see if that changes the min. Does that work better? I mean, it's still the same idea, so I don't know, but it is easier to program. Maybe I'm a little bit late on that. Maybe that is a cleaner way. Because then I don't have to figure out all this funky stuff with the path, and then just finding one of them that are good, and then that seems complicated, honestly. But if we change the edge 1 at a time, then maybe we're good. But then this is like such a whatever. But okay, fine, right? All right, let's rewrite it this way. The hardest thing is to, you know, but it is what it is. So okay, so let's say we shelf this, right? Then now we have for you and edges, right? And then now we go, okay, if this is -1, then maybe I just want it to be infinity, so I don't have to worry about the math. Oops. I don't have to worry about this thing. And also we can, we don't have to do the full graph. We can actually do like, it's greater than or equal to target. Maybe that'll speed things up a little bit. Okay, so then now we change this, and then now if we do a match, I guess. Yeah. If this is greater than it, we don't. That still means. No, that doesn't mean anything anymore, I think. If this is good though, then we just figure out the edges. We don't care about the path anymore. Let's get rid of this complexity. Also, like this is incorrect anyway. But okay. So then now, if it's equal to target, if it's too short, then we have to do something, right? I think that's the thing that we have to do here. If this is now too short, then what? Then can we just change it to the target? Is that a proof? Right? So okay, so it's target, then here. Yeah, just create a new list, right? Okay, so if it's equal to target, then we have edges equal to right? So then now for key in adjacency list of keys, let's call them U. For v in adjacency list u dot keys, then edges dot append u v adjacency list uv, but only if it's not infinity. But and also we probably should terminate this anyway. So if u is less than v and adjacency list, well, okay, fine. If u is equal to v, then yeah. If this is infinity, which is maybe I could just write, maybe infinity should just be 2 times 10 to the 9 or whatever it is, right? So then now we don't have to worry about that either. So then now we can just do this, and this is just for the symmetry reasons. Then we can return edges. Otherwise, okay. So this is equal to target. If we don't need this as part of the case statement anymore. If d is less than target, then we can actually just you know, delta is equal to d, right? Oh, what is this? Target minus d. What am I writing? And then adjacency list uv, we add delta. Adjacency list we add delta. Maybe we can actually convert this to a helper function of convert to edge list, adjacency list. So then now we can just have something like this here. And you can actually do this. Well, this never happens anymore because we changed it, but oh wait, no, that's just on the input, but we can just do it anyway on this thing. Okay, I have to make this a little bit up there. Okay, and then now in theory we should be able to do this, maybe by definition, but I can't assert this, right? So let's just I mean, I'm gonna write an assert just because why not? It's equal to target, because just for me learning, I feel like I don't have a strict proof for this, but I feel like that should be right. Maybe not. Did I miss something on it? And okay, let's give a quick submit. But I got it right last time, but I have no idea how to do it this time around. I was smarter last time, maybe. Maybe this time's out. Oh, that's even worse. Well, I still have no. I have an output, which is not great because that means that I'm generating output out of nowhere. But okay, at least it didn't time out, I guess. But what case am I missing? Okay, so how does this? What is this? The target is 8. I have to draw it out. Just to visualize this. Okay, so 0. Oh no, that's the output. This is the input. 0, 1 is -1. 1, 2 is -1. 3, 1 is -1. 3, 0 is 2. 0, 2 is 5. Okay, and we want to get from 2 to 3 in 8, but this is going to be 7, right? Isn't this addressed here? Maybe my match statement doesn't work, I don't know. Or maybe this is just way wrong. Because this should be here, right? But I don't know if that is my syntax or whatever. That is odd. Okay, so then now let's say we print this real quick. Yeah, I think that's right. In the last case, it's going to be infinity. Why is that infinity? Well, that's definitely wrong. Let's also print, just so that I'm making sure my cases are matching. Alright, that's really hard to read, but okay, fine. Yeah, but 0 connects to 3 and 2, and that should be good enough, right? What is going on here? Dun dun dun. So it's returning infinity. Did I mess something up with a typo or something? If it's -1 infinity, okay, no, that's right. Maybe my dice is small. D plus W is less than or equal to target. Is that the issue? Maybe I added that randomly, but with that, I don't think that should change things. No, okay, and I didn't expect that too, but that's just one of the things that we changed, right? So that's why. No, this is right-ish, right? I don't know. What's it called? Source, destination. I hope it's just like something silly because it is getting late. But yeah, okay, fine. 2, 3 is 2. 2, 3 is 8. But where does this come from? Am I just not returning right? Oh, I guess this is, but okay, but why? Because it's already, it should be already connected without the thing. So what am I doing? Dun, dun, dun. So then now it should be 2, 3 and then 2 billion. Don't know why this is printing multiple times actually. Oh, I guess from the other places, I guess that's fine. But what? Let's print out best. 0. Did I put 0? Am I dumb? I think I remember having a 0 somewhere. Oh no! Oh, this is this dumb thing. Okay, because I just assume everything's from 0. Okay, fine. I remember doing it, and then I just I don't know. And then where's the other print statement? Okay, fine. All right, let's give a YOLO submit. I mean, I mean, this is a thing. Okay, so apparently this works. To be honest, it's kind of, we'll read something about this cert because it just adds an extra texture, but that's not even a big deal. Yeah. Honestly, this is a tough one just because I think I got here the long way, but even though the other idea that I had is true, but this part of the proof I wasn't sure. But as soon as I have this part of the proof, then it becomes a lot easier. Like you could do some convergence things to make it go better, but in the worst case, this is going to be O of y times, right? So I don't know, right? So what is the worst time complexity for this problem, right? Well, this is the O of y, and Dijkstra is going to be, I guess in theory, in the early times it's still fast, but still, because we don't reach a lot of these things, and this thing filters it out. So if we didn't have this filter, how much slower would it be? Not that much slower actually. But yeah, I mean, obviously this is going to be O of y loop, and we do a Dijkstra for it. That's pretty. So basically, in a way, it is just about getting connected components. I wasn't able to prove this, but and there is actually like now knowing that this is true, which is that if there's a delta, we can just add this delta, then we can actually do one shortest path, right? And then do it that way with the number of, or you just do one shortest path with negative ones, and then kind of just convert all of them except for one of them to ones, and that will give you good enough. But yeah, I don't know. I don't know how to prove. I mean, I guess that like I know how to prove this. It's just I don't know how to prove the faster versions of this, which is kind of like iffy if you ask me. But this is O of y, right? And this is just a Dijkstra every time. This does not terminate if and it loops if it's still disconnected, right? So then now we're just trying to connect the graph in any way, or connect not the graph, just from source to destination. And there are a lot of ways to do that. And once you kind of construct one way to, and you could do that with, but I think there is just like some nuances in choosing the path, but this apparently is fast enough. So just what we said earlier, which is O of y relog y. I guess the thing is that the worst case is not easy to accomplish. Like I can imagine it's just like a full thing, like a one on top, a million in the middle, and all these edges. And I think one thing I would say though, in the shortest, one thing I would say is that because in the n squared graph, that means that maybe that is the thing, is that means that there are like graphs that makes it, the hops are not that high, right? So that means that maybe that's a little bit better. I think one thing that you can also do is shuffle this. Maybe that kind of makes the random, I mean, for this particular problem, unless they have like a ray whatever thing, I think it doesn't matter. Like if there's a case where it is targeted toward this, then it matters. But isn't it how to do shuffle? What I mean is that if there is and you can say an adversary, right? Then what is wedges? Oh, I made it into a set because I thought I would try to like look them up, but I guess now it doesn't have to be anymore. I forgot that I did change them to a set. But yeah, if there's an adversarial thing where okay, fine. I thought you could do it this way, but apparently not. You just have to do this, and then yeah. I mean, it shouldn't change the running time that much in this particular case, because I don't expect them to have like an adversary input to my thing. They could have been, but But and if they did, this will make it so that they can't really target you, right? So wait, let me double check real quick. Does this actually? Yeah, I guess it does. Okay, it modifies the original list. I just wasn't sure, but it seems a little bit slow, to be honest. I don't know if there's like a iterative tool or shuffle type thing. Maybe not. I don't know. She's a little bit slow. But in any case, yeah, then if they have a test case against you specifically, if you add something like this, it'll make it so that, you know, well, they can't really anyway. It'll eventually converge, though apparently it still adds a bit of running time. What did I do last time? Well, last time I did a lot of cray. I guess actually I end up doing mostly the same. I have a, which is kind of, I don't know. I'm curious what I did last time. I mean, get answer is fine. This is what I did, right? Max is here. Okay. Well, I mean, actually, I guess I end up doing basically the same. I have target. It was bigger than target. Oh, I did a binary search. I don't know why I guess I do love binary search, but apparently it's not even necessary because you could just, this is just what, I mean, this time I actually didn't even think about it. I know that I talked about binary search a little bit, but I actually did not talk about think about it if that was not the thing, right? I guess I should have thought about it, but what I mean is that if this thing did not assert force or it asserts force, I might not have thought about binary search to get the answer to this one. That makes sense. I mean, well, I mean, it makes sense because this works, but I don't know. I'm curious about the hints. I don't know about this. This is a hard one, honestly. I mean, I know that I got it, but it's still hard. I mean, I think the hard part is just to prove I mean, this solution I was mostly there early on, but I just wasn't confident about it. But let's take a look at the hints. Right. Yep. All right. Yep. Got it. Yep. Got it. Oh yeah, I guess I could have checked that for an earlier. I guess one thing I didn't do is I changed all of them to once to do the check to early terminate, but I guess that's not a big issue. I mean, yeah, that's obvious, but I guess that's what we kind of did, but I don't know that I think I just want a proof on it. That's all. That's a little bit slow. I mean, I don't know why they had to do two quote unquote solutions with min heap and regular heap. I think someone has said that Alex has mentioned that they do get paid per word on a solution. That's why there's all this crap. But yeah, I guess there's multiple ways of doing it. But I think for me, the more interesting, the harder part is the proofs. I and also that this is fast enough. Read times or this thing is fast enough, which I don't know. This is apparently 9 minutes ago. Is it 20? I mean, I don't know. I mean, the problem is not, like I said, the problem isn't that this problem is difficult. Or like, phrased another way is that I think the solution is not that bad to kind of reason to, but it's just that the proofs are hard, and I don't know that I'm satisfied with whatever proof that they kind of mentioned here. I mean, they kind of just gave an algorithm, but maybe this thing has a proof. I mean, just put some intuition. I mean, these are just like filters, right? Which we already did. But I'm not. In an algorithm, but I don't see a proof, so I don't know. Anyway, yeah, that's all I have with this one. I might rewatch this one. I don't know if I did it during contest. Did I do this during contest? Maybe I did. I feel like I was more. I don't know how to check, but maybe I did it virtually either. But I would also say that, like I said, during contest, I would have YOLO'd this a long time, like maybe 20 minutes earlier than I would have, just because I don't know that, like, it's on the borderline of good enough. But I would also say that my initial idea, while true, because it is a subset of what I end up doing, it's just so hard to get to program correctly, which is why I kind of hesitate. But with clarity, I was able to kind of think about this new way, which is like the same idea but going from the other direction, which the coding is much easier. So there is something to be said about thinking through the problem and thinking through the coding and all this stuff. But I don't know. Yeah, that's all I have for this one. That's what I have today. I'm not going to do an extra problem today. It's an hour and 12 minutes. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.